Alright, welcome to Mathematics Lifeline. This video is an introduction to the calculus limit. So there's an important distinction that we need to make, because in algebra what we always learn with functions is to find an exact y value to find the exact value of the function. In calculus, a lot of the times we're not as focused on the exact value as much as we are an approximation. So what a limit is saying is that as you get closer and closer to a point, as you get extremely close to a point, what is your y value approaching? You'll never actually get to the point. That's for algebra. In calculus, we're talking about getting closer and closer and closer. That's what this note down here means. It says limit means near, not at. So when you're evaluating a limit, you're not evaluating the exact function value, you're evaluating where the graph is getting closer and closer to. So let's take this function as an example. This is f of x, and we're asking ourselves, what is the limit as x goes to 3 of this function? So here's your x value of 3 right here. We see that we have a defined point at y equals negative 2, and we have a hole at y equals positive 2. So what our limit is saying is when you're getting closer and closer to 3, what is your graph approaching? So we look at it, we're going up, down, and over right here we're heading towards 3. We see that our y value is getting closer to this 2 value. Same thing if you come from this direction, you're getting closer to this 2 value. So because limit means near, not at, the value of this limit is going to be 2. Now in algebra, if they asked you what f of 3 is, that would equal negative 2 because the graph is defined at negative 2 at that point, but that's not our limit. Our limit is positive 2 because that's where the graph is approaching. There's also two other ways we can write this. We can write it as the limit as x approaches 3 from the positive side, and the limit as x approaches 3 from the negative side. So what this is saying is from the positive side right here, it's saying for anything to the right side of the graph. So you see that this arrow is saying it's going out to infinity in that direction. So what the right side means is you're coming from this right side and you're asking what y value is this approaching, and we see that right here that's 2. So that matches with this limit. And now from the negative side, that's the left side of your point. So when you come all the way up here from infinity over to your point, you see that you're still approaching 2. So if these two are the same, then it proves that that limit is right there. Now there are cases where your positive and your negative side are going to be different, and that means that this limit is undefined. Let me show you. So let's make a new function. This is f of x. Let's say we have something that looks like this, and then we'll say we have something that looks like this. And we're trying to find the limit as x approaches 0 f of x. So we know from the last example that we can split that up into two separate things. So let's do that. Let's say what is the limit as x approaches 0 from the positive side, and what is the limit as x approaches 0 from the negative side. So let's look at it from the positive side. So we're going to start out here, and then we're going to come in to this x value of 0 right here. We're coming in from the right side, and we see this is going up, infinitely up. It's going to go all the way up to infinity because you've never seen into this graph. So your limit here, your graph is approaching infinity, so your limit is going to be infinity. So now let's take it from the left side. So the left side, you're coming in from negative infinity, you're coming down, 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 and you see it's going to keep on going down. It's never going to touch this 0. So if you're looking at the f of 0, right, f of 0 is undefined. Because your graph, you see, will never touch the y-axis because there's an asymptote there. So right here, if we're looking at it from the left, you see we're going all the way down, but we never touch it, so we're going down to negative infinity. So that tells us that we have a limit from the right side that goes to infinity, and a limit from the left side that goes to negative infinity. That doesn't add up. We can't do that. Because that says that we have no limit here, because your limits going to both sides of this value are completely different. So we can't say that that limit is equal to anything. This limit, d and e, does not exist because you cannot point to a specific value. Now let's try one without the infinities. Let's say that we have a new function, f of x. We've got a hole here, it goes off to infinity. We've got a closed point here, goes off to negative infinity. This is at 1, this is right here is at 3, and this is at 1. So what we're asking ourselves is, what is the limit as x goes to 1 of this function? So we know that we can split it up into positive and negative, so let's do that. Limit x goes to 1 from the positive side, and the limit as x goes to 1 from the negative side. So let's start with the positive side. So we're coming in from this infinity value, and the whole time, because this is a straight line, the whole time our y value is this 1. So as you're getting closer and closer to 1, you see that right here it's not defined. At 1 it's not defined, but we're talking about near, not at. So we see that our limit from the positive side is just going to be 1. Now we go from the negative side. So we start out here at negative infinity, we come in, we see that the whole time this is at the y value of 3. So as it gets to 1, it's going to stay there. It's going to stay at 3. So now, what is the limit as x approaches 1? Well, we have a difference in our limits from both sides. This is 1, this is 3. So we can't say that we have a limit because it's different coming from different sides. So this again is d and e. If these were the same, then we could say that the limit was the same as what these are. But it's not, they're different, so the limit does not actually exist. So now that we've done some graphical examples, let's go ahead and solve one algebraically. So let's say that instead of just f of x, we say that f of x is equal to 2x minus 4, right? And we want the limit as x approaches 3 of 2x minus 4. So there's nothing really that fancy here. The only thing you have to do is plug in your 3 for your x and solve it out. So you have 2 times 3 minus 4, which is 6 minus 4. Your limit here is 2. Now you can prove this on a graph, so let's go ahead and draw that out. So this is your f of x, which is 2x minus 4. We know that our y-intercept right here is going to be at negative 4. We have a slope of 2, so it's going to look something like this. It's not perfect, but it's close enough. We'll say this is 3, this is 2, that's 1. And we'll say that we have a y value up here, that's your 2. And then you see our point here at 3, when you go up to 3, it's going to touch the graph at the positive 2. Which means that from the left side of the graph, so from your negative side, you're going up and you're still approaching 2. The right side of your graph, you're coming down and you're still approaching 2. So we know that if we split this up into 3 from the positive side and 3 from the negative side, they would be the same. It would still give you 2. So any of these examples you can show graphically. It all works out the same way. So let's do another example. Let's say that our new f of x is equal to x squared minus 7. Let's try that. And we'll do the limit as x approaches 4 of x squared minus 7. So again, all you have to do here is just plug in your 4. So we plug in our 4, we get 4 squared minus 7, 16 minus 7, 16 minus 7 is 9. That works. That is the right answer. If you graphed x squared minus 7, it would look something like this. And you would see that the limit as x approaches 4 of this graph, it would be up at 9. You can graph that on Desmos, you can graph it on your calculator, you can graph it anywhere. You'll see that as you get close to this positive 4 value, be somewhere over here, it would be up here at 9. You can graph any of these examples. So let's try a different example where you may not get an exact answer. Let's have f of x equal to this. X minus 1 over x squared minus 1. And we're going to have the limit as x approaches 1 of x minus 1 over x squared minus 1. So now I know you're thinking, let's go ahead and plug in our 1's. So okay, let's do that. Here's a 1 going right here, we got a 1 going right here. This is 1 minus 1 on top over 1 squared minus 1, which is just going to be equal to 0 over 1 minus 1, 0 over 0. We can't do that. 0 over 0 is undefined. Anything over 0 is undefined. So this right here, we know is going to be undefined. So what can we do with this? We're going to have to alter this question so that we can actually find a limit. So let's try it again. Let's say we have the limit as x goes to 1 of x minus 1 over x squared minus 1. What we can do here is factor the bottom. So we know that x squared minus 1 is the difference of squares. So x squared minus 1 is the same as x plus 1 times x minus 1. If you FOIL that out, you see you'll get x squared plus x minus 1. These right here cancel. You end up with x squared minus 1. So this works. That is how you factor that. So let's go ahead and change the denominator into this factored form. So we'll say that this is really the limit as x goes to 1 of x minus 1 over x plus 1 times x minus 1. Now we can simplify this a little bit because we have an x minus 1 on the top, we have an x minus 1 on the bottom. Let's go ahead and cancel those out. So now we really just have the limit as x goes to 1 of 1 over x plus 1. Now we can plug in our value of 1 in for x. We plug that in, we get 1 over 1 plus 1 is equal to 1/2. And that's going to be your limit of that function. So sometimes you're going to have cases like that. Sometimes you're going to have cases where you have to manipulate the top or the bottom so that you don't get 0 over 0 or anything that you can't determine. That's the problem with limits. But the main point of this lesson is limits are crucial to calculus. Limits is a fundamental part of calculus. You have to understand the idea that you're not exactly looking for the exact value of the function. Because you'll see here, if you were to graph this, there's an asymptote at x equals 1. So you have to find what that limit is. That's 1/2. So it's really important to understand the concept of limit means near, not at. You're not always going to get the exact answer of a defined function because this is a limit. It means you're getting closer and closer and closer, but you never actually get there. And as long as you understand that, you're going to understand limits. So that's going to be it for this video. I appreciate you for watching. And as always, let me know if there's any questions or concerns.